So let's deal with supplemental problem 250. You can find this problem in the ECE302 ebook in the Chapter 2 Supplemental Problems, starting on page 29. A Panasonic Model RX FT560 portable 14-watt stereo uses a 12-volt power supply with batteries. I removed the batteries from this stereo and hooked up a lab power supply and began to measure the current when I set the voltage to 12 volts. And I found that at full volume, where I had max treble and min bass, I had the most current, about 1.4 amps. And then when I played with all the knob settings, the lowest I could get was about 200 milliamps, and again at 12 volts. I'd like to design a full-wave rectified power supply, and let's use a 9.5 2-to-1 transformer, and these are what are called 12.6 volt transformers, and they take line voltage and bring it down to 12.6 volts RMS. These are commonly used in vacuum tube power amplifiers, so they're fairly inexpensive. Assume that the outlet voltage is 120 volt RMS at 60 Hertz, and let's use 1N4001 diodes, and I looked at the data sheet, and the drop across the diode is about 1 volt at 1.4 amps. I'd like you to pick the value of C sub L such that Vout has a maximum ripple of 1 volt peak to peak. I'd also like to solve for the average voltage of the output, which would be uppercase V with uppercase O. And likewise the average diode current as uppercase I, uppercase D. Then add a series resistor to the secondary of the transformer to limit the surge current to approximately 10 amps, if the secondary winding resistance is about 400 milliohms. Then using PSpice, could you plot the output voltage and the surge current for the minimum and maximum values of the load? Also measure the average voltage and the ripple voltage peak to peak. Lastly, look up the datasheet of the 1N4001 diode and check to see if you have exceeded any of its ratings. But from the 12 volt data that I collected, I found that the current maximum was 1.4 amps and the minimum was 200 milliamps. It was all at 12 volts, so I can approximate the stereo as 8.57 ohms and 60 ohms. Now let's go back to page 60 of Chapter 2 class notes and let's pull up the power supply, giving a transformer specification of 9.5 2-to-1. We're going to use 4 1N4001 diodes, pick a capacitor, and here we've got the stereo, which varies from 8.57 to 60 ohms. The lower the resistance, the more ripple you have. So this is our worst case to satisfy. Here's the input to the transformer, and here's the secondary, the output. Let's solve for the maximum value here. We're going to use that in some of our formulas. That's going to be equal to the input maximum divided by the turns ratio. And the maximum of the input is the RMS value times the square root of 2. 120 times the square root of 2 over 9.52 is 17.83 volts. Take 120 and divide by 9.52, you get 12.6. As I said, this is called a 12.6 volt transformer. So back in our class notes, again on page 60 of Chapter 2, there was a summary. One of those was the ripple voltage. We know everything here but the capacitor, and we've specified the ripple, so we can solve for the capacitor from this equation. Let's do that. Here I've got the capacitor value. I'm going to bring that over here and divide this over here. So here's this term in the numerator divided by the ripple. Maximum secondary voltage was 17.83. The drop across the diode is around a volt, so minus 2 times 1 volt. I want a ripple of 1 volt peak to peak. Here's the 2, here's 60 hertz, and here's my 8.57 ohms. It's going to give me a really big capacitor of 15,393 microfarads. The nearest standard value is about 16,000. Let's calculate the average voltage at the output and the average diode current when the load is 8.57 ohms. Back in Chapter 2, page 60, we had a formula for the average voltage. It was V sub S maximum minus 2 diode drops minus ripple over 2. 17.83, 2 times 1, and then we had 1 divided by 2, and that's 15.33 volts DC. The average diode current is half the average output current, which would be the output voltage DC divided by R sub L, 15.33 divided by 8.57, about 894 milliamps. Let's also calculate the same results but with a load of 60 ohms. We need to calculate the ripple. That's going to be from, again, page 60. This is V sub S maximum minus 2 times the diode drops divided by twice the frequency, R sub L and C sub L. It turns out to be 137.4 millivolts peak to peak, and much smaller than the case with the 8.57 ohms. This is our worst case for ripple. For the average voltage, V sub S maximum minus 2 times 1 volt, and then my ripple divided by 2 gives me 15.76. A little higher DC voltage and have a larger resistive load. And the average current is 1/2 V out over R sub L, 5.76 now over 60, 131 milliamps. Likewise, from that page 60, we had a formula for the surge current. It's V sub S maximum minus 2 diode drops divided by R sub S. We want to pick the value of R sub S to limit the current to 10 amps. We've got a V sub S maximum 17.83, 2 times 1, and then we want to have a 10 amp maximum. That gives me about 1.583 ohms that I need to add in series. I already have about 400 milliohms of resistance, so I can subtract that off from the 1.583, and that's 1.183. The nearest standard resistor is a 1 ohm resistor, so let's just stick a 1 ohm resistor here. I have my design. The value of C sub L been picked for the different values of R sub L to have no more than a 1 volt peak-to-peak ripple. Let's do a SPICE simulation. I'll call this one node 1, node 2, node 3, 0, and node 4. And I'm just going to use a sine wave here to represent this part of the circuit. Here's my SPICE file for my design. I've got a title, a dot end. I have a voltage source that's a sine wave. I've got a resistance in series. I'm going to have to add in the winding resistance because my voltage source is perfect. 4 diodes, capacitive load of 16,000 microfarads, and a resistive load of 8.57 ohms. I'm going to use the model we did in Supplemental Problem 2.5 for a 1N4001 diode. And then I'm going to plot this in steady state. So I played with this a little bit, but eventually settled on 24 cycles. 1 over 60 hertz would be 1 cycle, and multiply that by 24 and you get 400 milliseconds. I'm going to divide this by 2,000 to get more data points on the screen because there's a lot of sharp activity going on here. Start printing at 0. Make the sealing step the same as the print step. And I also want to have the capacitor initially at 0 volts. What the program does, if you don't say anything, is it actually has to find the initial condition. I'm going to set that equal to 0 by using user initial condition because there's nothing specified here. It's set equal to 0. I want to show the surge, so I'm going to do a cosine wave. Here's my sine wave. It has an average value of 0, a peak value of 17.83, frequency of 60 hertz, and this next number is called a time delay. You can delay the start of the sine wave. And this is an exponential envelope. It's called a damping factor. Talked about this a little bit in ECE302m. And then the last number here in PSpice, but not in the SPICE program, is the phase angle. I'm going to put 90 degrees here to make a cosine function out of my sine function. Ran the simulation, and here's my output voltage. And you can see I reach steady state. My ripple peak to peak is 329 millivolts, and my average voltage is 10.378. In other words, halfway between the max and the minimum. It's a lot smaller than what I had calculated for the average value. I was expecting 15.33, but remember I've got this series resistor now, and that's creating a voltage divider in my results. And my ripple likewise is a little bit smaller. I was shooting for 1 volt peak to peak maximum. It's actually smaller than that. So that's a better result. This is not as good, but I have 10.378 volts here instead of the 12 volts I was shooting for. This is surge current in diode D2. To get a surge here a little bit more than 10 amps and eventually goes down to something less than 4 amps. Run the file again, but I changed the resistor now from 8.57 to 60 ohms. And you can see from the same simulation, I have a much smaller ripple. In fact, it's only 85.05 millivolts peak to peak. And the average voltage, this is halfway between the max and min here, is 14.1165. I was expecting 15.76. And again, I've got a series resistor in the lead of the secondary of the transformer that's causing a voltage divider. The surge current doesn't depend on the resistive load, so you can see here that that surge is still 10.009 amps. As you go higher in cycles, this drops a lot lower because my resistive load is higher than the previous case. Let's look up the 1N4001 datasheet in that reference at the beginning of the supplemental problem. Take a look at page 1-85. It's shown here. I marked in the maximum ratings the following. This is the peak repetitive reverse voltage. So the most I can have across it is 50 volts, negative. Then the average rectified forward current, 1 amp. And then the non-repetitive surge current is 30 amps for 1 cycle. Let's go back and take those numbers into our results. Those are the 3 things I have here. I went back and I changed the .tran command to print the last 100 milliseconds. In other words, to get the results in steady state. I'm still going to end at 400 milliseconds, but I'm going to start saving data at 300 milliseconds. And then take the difference of these two and divide by 2,000, and you get 50 microseconds for the print step, and make that the same as the sealing step, and again use the user initial conditions. This is just simply getting the simulation and getting that last part in steady state. We have 2 resistive loads, 60 ohms and 8.57. I want to look at the voltage across diode D2. You can see it gets forward biased and it gets reverse biased. Let me just go back to page 31 and show you how we can predict the value of this. Looking for the voltage across here when this is off. This node voltage here, if this is forward biased, this is going to be VD on. Here back to ground, something close to 1 volt. This would be minus 1 volt, and then minus this node, which was 14.1165 volts. Let's go back to page 34. The minus 14.1 volts, and I've got the drop across the diode. The reason I picked this case here is because the output voltage is the largest when I have the largest value of the resistive load. This number would, in magnitude, go down if I were to use the 8.57 ohms load. So this is the worst case. I can have 50 volts across the diode when it's reverse biased. I have here only 14.97. Then what's the average current in the diode? I started at 300 milliseconds. Let's add one period, which is 16.6 milliseconds to the start. That would be the average value, about 600 milliamps. Our design has a repetitive reverse voltage of about 15 volts, a non-repetitive peak surge current about 10 amps, an average rectified forward current of 599.319 milliamps, all of which fall under the maximums of the 1N4001 diode. One last comment, even though our DC output voltage at full load is only 10.378 volts instead of 12 volts, the power supply will still work because of the voltage range of partially discharged D-cell batteries. Dropping to 10.378 volts means it will have less power out. However, my true concern about this design is the large capacitor that we need for C sub L. In Supplemental Problem 3.19, we'll revisit this design and address this. And this is Supplemental Problem 2.15.